this week Dr. Tayler Clarke. She studied biology in the University of Costa Rica. Later, she did a master in integrated coastal zone management in the same university in Costa Rica. She now recently finished her PhD in the University of British Columbia, working on climate change, and I think this is what she's going to talk today. Dr. Clarke has a lot of experience in artisanal fisheries and troll fisheries, and in recent years in aspects related to climate change subsidies. So he's a very experienced person, and we're very happy to have her here.
Thank you very much, Andres, for that kind introduction and for inviting me to be here with you virtually today and to share with you a little bit of the results of my thesis, as Andres said. And I actually just defended it a couple of weeks ago, so it's pretty fresh. So I focused mainly on the impacts of climate change on the marine resources in the Eastern Tropical Pacific. And we know that climate change are going to be, or are expected to affect fisheries in the tropics the most. And this is where we expect to see the largest losses in potential fisheries catches and fisheries revenue. At the same time, in the tropics, where we expect to have the high climate impacts of declining catches, shrinking fish, loss of different species, it's also where people depend more on the oceans, more on these fisheries for employment, revenue, and food security. At the same time, most of these fisheries are data deficient. So if you want to study the impacts of climate change on these fisheries, you have to use data deficient methods that can be applied despite this lack of information. And we know that to reduce the impacts of climate change on fisheries, we need to work with climate change mitigation and sustainable fisheries management. Those are the things that are shown to have the biggest impacts. However, even if we stop all greenhouse gas emissions right now, then we're still going to have this residual effect of climate change, and we're still going to need to adapt our fisheries to these changes. And so no matter what, we're going to have to begin incorporating the impacts of climate change into fisheries management. And this is going to have a regional approach to studying these impacts, because the magnitude of the changes and the direction of species shifts can change a lot from one region, from one country to another, as you will see in these results. So as the title says, I focus mainly on the Eastern Tropical Pacific, which I define from the Gulf of California in the north to northern Peru in the south. And this definition was based on the biogeography of fishes from work carried out by Robertson and Kramer. The Eastern Tropical Pacific actually has really interesting regional oceanographic dynamics, in that it has very cool surface waters in the north and in the southern regions. And this is because of the California current upwelling in the north and the Humboldt current upwelling in the south, and the equatorial upwelling current as well. So these bring cooler waters from the bottom towards the surface. And if you're a fish along Central America, it creates sort of a reverse temperature gradient, because if you're going to be headed towards the equator, then you're actually going to be experiencing cooler and cooler temperatures as you head further into the tropics, which is completely the opposite from what we would expect if we were in the tropics and other places in most other parts of the world. The Eastern Tropical Pacific also has large oxygen minimum zones with oxygen concentrations below 0.05 to 0.08 moles per cubic meter. And it also shows up very close to the surface. So you can see that along the coast of Central America, it can even reach up to 40 meters below the surface. And in the region, it's generally below 100, above 100, 150 meters. So what this means is that the oxygen minimum zone is well within the continental platform and will be affecting the life that inhabits the continental shelf. These oxygen minimum zones have very large functionally anoxic cores, and just as most other oxygen minimum zones throughout the world, they are projected to be increasing. So we can see here that they've been increasing since the oxygen minimum zone have been expanding towards the surface, mainly since the 1980s. However, you can also see that there's a wide variability within the time series that might be obscuring long-term trends. So I started out by taking a very broad approach and projecting the impacts of climate change on living marine resources in the region. I began with a species distribution modeling approach, and I used temperature, oxygen, pH, primary productivity, salinity to project the changes in the environmental conditions that the species would be facing in the future. And I focused mainly on 505 species caught by the main fishing fleets in the regions, which include small-scale fisheries, fisheries for large and small pelagics, and the shrimp trawl fisheries, which I separate into the bycatch and to the target shrimp species. So one of the main results here was that species that are caught by all fleets shift in the same direction, just with different magnitudes. And along Central America, as would be expected, the fish are actually shifting towards the cooler waters brought up by the upwelling systems in the Humboldt Current and in the equatorial upwelling system along the equator. On the other hand, in the northern and in the southern parts of the Eastern Tropical Pacific, fish are actually shifting towards the poles, as is generally projected for shifting species worldwide. And so this really highlights the need to take a regional to local approach to study the impacts of climate change on fisheries. I also found that species are projected to shift. This is by mid-century under RCP 8.5. Species are projected to shift towards shallower waters. This is contrary to what we would expect in most of the world, or what has been reported for fish in most of the world, where fish are actually shifting towards deeper waters following the cooler temperatures. However, here we have the presence of these oxygen minimum zones that are limiting the distribution of fish and that are actually expanding, so they're squeezing fish towards the shallower waters along the coastline. And one thing that you will notice is the pretty wide difference in the range of the depth shifts for each country. And when I compared that to the actual depth of the oxygen minimum zone, the countries where the depth shifts are lowest, with the exception of Galapagos, are where the oxygen minimum zone is the shallowest. So, for example, along Central America, the oxygen minimum zone tends to be very shallow, and the depth shifts occurring per decade are projected to be smaller than within the rest of the region. The changes in habitat suitability generally reflect the direction of species shifts, and these maps represent the changes in habitat suitability that we would expect for the main species caught by each fishery by mid-century relative to the beginning of the century under RCP 8.5. So we can see that for most fleets, the highest impacts can be seen between southern Mexico and Panama. Habitat suitability losses can reach up to 50% in some areas, and catch losses are expected for all fleets. So you see that the habitat suitability for shrimp is expected to increase a little bit, but then the habitat suitability of the actual trawl bycatch is expected to decrease quite strongly.
Tate,
Yes?
there's a problem with the slides. We're stuck in slide number 9, and it's
Oh
not.
no.
It's not going. I don't know if maybe you stop sharing and do it again, or I don't know how can we solve this.
I'll stop sharing and oh no, the computer is stuck.
Yeah, don't worry. Or I don't know if it is also that the system is trying to share your video and it's not working. Maybe if you stop your video.
Andres, can you please make me the presenter so I can share the screen? Thank you. Okay, are you able to see the presentation now?
Yeah.
Okay. I'm really sorry about that.
Don't worry.
Okay, so just to refresh, this is the slide showing the different depth shifts for countries within the region, showing that species are projected to shift towards shallower waters. And this is here's where I showed where countries with the smaller depth shifts actually are located where the oxygen minimum zone is shallowest. So these were the habitat suitability maps that I was talking about that show the changes in habitat suitability by mid-century relative to the beginning of the century under RCP 8.5. And you can see that the highest impacts are between southern Mexico and Panama for most fleets. And the habitats become up to 50% less suitable for species within each fleet. So in this first sweep, I took a correlative approach to study the impacts on marine fishery species in the region. And this revealed the importance of warming and deoxygenation on fisheries. But we know that although the species distribution modeling approach is very widely applied to study climate change impacts, it is really good at projecting species distributions in the present, but we don't know how well it's going to perform when projecting into novel climates, as we would expect will begin to occur within the tropics. So this is why for the next step, I developed a mechanistic approach to study the impacts of warming and deoxygenation on marine organisms. And it was based on an approach that links changes in temperature and oxygen with species biogeography, growth, and metabolism to create an indicator of habitat viability. And this method is based on the idea that oxygen is a limiting factor for fish in water. And this is because it has a much lower oxygen concentration. There's a much lower oxygen concentration in water than in air. And it's also harder for fish to extract oxygen from the water because water is much more dense and viscous than air is. It's also based on the fact that warming increases the metabolic oxygen demand for marine ectotherms. We know that with the type of warming that's expected under climate change and marine heat waves, metabolic oxygen demand actually increases exponentially with temperature. However, over evolutionary time periods, species have been able to adapt to the warmer temperatures within the tropics by actually reducing their minimum metabolic oxygen demand. So what that means is that at a reference temperature, a temperate species is going to have a higher metabolic oxygen demand than a tropical species is. And so we know that temperature and oxygen partially shape the species aerobic scope, and that is the aerobic scope can be defined as the difference between the minimum metabolic rate of a species and the maximum metabolic rate. Warming is projected, this aerobic scope generally determines the amount of different oxygen limiting processes that can occur within an organism at the same time. So this would mean things like growth, reproduction, movement, feeding. And we know that warming is going to compress the aerobic scope by increasing the minimum metabolic rate, while deoxygenation reduces the aerobic scope by reducing the maximum possible metabolic rate for species. So this compression may lead to trade-offs across oxygen demanding processes and then affect the fitness of marine ectothermic organisms. So based on these ideas, we developed an aerobic habitat index, and this uses biological principles that relate species growth and metabolism to their environment to be able to understand the impacts of warming and deoxygenation on marine ectotherms. It's essentially just a ratio of oxygen supply in the environment to oxygen demand by an organism. And so it's an ecophysiological indicator of habitat viability. If you assume that a habitat is viable, if it has more oxygen in the environment than the organism actually demands. So warming would reduce the aerobic habitat index by increasing the oxygen demand, while deoxygenation would reduce the aerobic habitat index by reducing the oxygen supply. This particular index that we developed is based on the von Bertalanffy model, and so some of the key inputs are the K, von Bertalanffy K and W infinity, or L infinity, that are available for thousands of marine fish and invertebrates. To be able to assess the performance of this index, I then compared it to a previously published metabolic index, and I was able to compare these two because they're both ratios of oxygen supply to demand, and I had such high confidence in this previously published metabolic index because it's based on physiological experiments that determine oxygen thresholds at different temperature levels. So it's based on experimental data. And both of these indices relate the values to species distributions through biogeographic and climatic data. The next approach was to actually make the comparison and actually project the risk of species habitat loss for different species. The data available to compute the metabolic index is it's not available for a lot of species. So I chose sea bream, cod, and red drum, none within the Eastern Tropical Pacific, but it was because of data limitations. And we can see that overall, both methods actually do predict habitat losses in very similar places. This would be by end of century under RCP 8.5. And also, if you compare the percentage of habitat losses for each one of these species based on their baseline habitat area, the differences remain between 1% across each indices. So based on these results, I concluded that the aerobic habitat index can be used to estimate the impacts of warming and deoxygenation on marine fishery species. But then we have to take these impacts of warming and deoxygenation that occur on the organism level and translate them up to the population level, where we would expect it to change population sizes, species distributions, and that the different sensitivities of species to these stressors would cause changes in community structure and trophic interactions that would eventually be reflected in changes in catch composition. So the end goal is to see how warming and deoxygenation actually affects catch composition. And we know that warming has been affecting catch composition worldwide as temperature warms. The average temperature preferences of species in the catch increase, with the exception of the tropics, where it eventually reaches a plateau because only tropical species remain within the catch. But the question is, what is the role of oxygen limitation driving these changes in catch composition? And based on everything that we've just discussed, I would assume that the catch composition would go from being dominated from cool adapted species with high oxygen demands, which their abundance would eventually decline, and the abundance of warm adapted species with low oxygen demand would increase, and catch composition would eventually be dominated by warm adapted species with low oxygen demands. I then applied this framework to study the impacts of warming and deoxygenation on pelagic fisheries in the Eastern Tropical Pacific. And I did this based on two catch or community-based indicators. The first one was the mean aerobic habitat index of the catch, and it's essentially just a weighted average of the aerobic habitat index of different species weighted by their catch. And it should be an indicator of physiological performance of a species. However, this indicator is going to include two different opposing trends. The species responses to warming, where we would expect oxygen demand to increase with temperature, but also it's going to include how species have adapted to the latitudinal temperature gradients as species shift and the catch compositions change. So there we would expect mean oxygen demand to actually decline along temperature. So to be able to tease out these two effects, I use the mean oxygen demand of the catch, which is essentially the average oxygen demand at a reference temperature of species weighted by the catch. And it is an indicator of catch composition. It would just be representing the way that species have adapted to the latitudinal temperature gradients. But how do we interpret changes in both of these indicators in pelagic environments? And to do this, we need to first understand the trends that go into these changes. So the metabolic oxygen demand at an average temperature is expected to decline along temperature if we're talking about latitudinal temperature gradients, and then the metabolic oxygen demand is expected to increase with temperature when we're talking about warming by climate change and marine heat waves. So the end result of that is the MODC, which represents the warm adaptation in fish populations that I would expect would decline in subtropical regions as species with high oxygen demands represent lower and lower proportions of the catch. And in tropical regions, this would eventually plateau as only species with low oxygen demands remain. And then because of the change in catch composition, the aerobic habitat index of the catch would increase in subtropical regions and then begin to decline in tropical regions as the warming increases in metabolic rate take over as the main driver of the trends in this indicator. So combined, I expect both these indicators to give us an idea of how and why catch composition, or finding the signals of warming and deoxygenation in changing catch compositions. So I applied it, as I said, to the Eastern Tropical Pacific, but to understand the results, let's review how temperature and oxygen changes within the region. General temperature varies between 23 and 29.3 degrees Celsius, and the average annual oxygen concentrations are mainly at saturation. We're talking at about surface oxygen here. And the northern and southernmost EEZs have the lowest temperatures and highest dissolved oxygen concentrations. So these are the actual results showing the effects of temperature and oxygen on pelagic fishery resources in the Eastern Tropical Pacific between 1970 and 2009.
Okay, we have the screen frozen again.
Oh no!
In slide 27.
No. Okay. I stopped sharing. Well, this is unfortunate.
Yeah, I still see the slides.
Okay, I'm going to sign out and sign back in. That seemed to work last time because it's not letting me stop sharing.
Okay.
Okay.
for the technical difficulties, Taylor is trying to connect again. So we'll give her a couple of minutes.
Okay, can everyone hear me?
Yes.
Thank you very much. And I'm really, really sorry about these delays. I'm gonna turn my my video off to see if that helps a little bit. So, in what slide did we drop off?
Yes, 27.
27. Okay. So explaining how to interpret the trends in MODC and HIC. So basically, just to understand how to interpret these indicators, we need to understand what the trends that are the processes that are causing these trends. And that is that at average temperature, the metabolic oxygen demand declines with temperature when we're talking about the latitudinal temperature gradients. And then the metabolic oxygen demand increases with warming. So MODC mainly represents warm adaptation in fish populations, and it declines in subtropical regions as species with high oxygen demands in the catch become less and less abundant. And then in tropical regions, this trend eventually stabilizes as only species with low oxygen demands remain. Then the aerobic habitat index of the catch would be representing both the warm adaptation in fish populations and the warming increases in metabolic rate. In subtropical regions, the warm adaptation is the trend that dominates. So the aerobic habitat index of the catch would be increasing with temperature in subtropical regions as due to the changes in catch composition. But in tropical species, then warming increases and metabolic rates becomes the main driver behind the trends as the gap between oxygen demand and supply narrows. So both of these indicators, I expect, would be able to allow us to understand a little bit better how warming and deoxygenation is affecting catch composition. And the temperature and oxygen gradient within the Eastern Tropical Pacific is actually, we have to understand it a little bit to be able to interpret the results. And that is mainly that the northern and the southernmost exclusive economic zones have the lowest temperatures and the highest dissolved oxygen concentrations. So here I am showing you the actual results showing the effects of temperature and oxygen on pelagic fishery resources in the region. These are the pooled time series for HEEZ between 1970 and 2009. And the dots represent average conditions in each country. So as expected, within the cooler temperatures, the catch composition is changing towards species with lower and lower oxygen demands until you reach a threshold of around 25 degrees Celsius, when the oxygen demand of species in the catch stabilizes and only species with low oxygen demands remain. Then we have that the aerobic habitat index of the catch actually increases in cooler temperatures until it reaches this threshold of 25 degrees Celsius, and then it begins declining in tropical countries. So I expect that temperature is the main driver of these changes in pelagic fisheries. However, we do see an opposing trend between the indicators and oxygen, but I expect that this is just because of the strong negative correlation between temperature and oxygen at the surface layer. But I do expect that oxygen is playing a key role in driving the thresholds or the temperature and oxygen breaking points that we see in these graphs. And I think that maybe the oxygen thresholds may represent tipping points. I say this based on the graph on the left that represents the amount of changes in physiological performance that are needed to drive changes in species composition. In countries where oxygen levels are far from the threshold, the slope between both indicators is stronger than in countries where oxygen levels are close to the threshold. And that means that in countries close to the oxygen threshold, smaller changes in physiological performance are needed to drive changes in species composition. This means that catch composition is more unstable in these countries and might react quicker to things like El Niño or La Niña, for example. And there is actually some evidence within the region supporting the existence of these thresholds. Oxygen wasn't measured, but temperature was. In fisheries, in pelagic fisheries in Ecuador, they found that the equatorial front that we see right here, it represents it separates warmer and cooler waters, and the threshold mainly for separating the different fisheries with different catch composition is 25 degrees Celsius. So in warmer water than that, fisheries tend to catch tuna, billfish, and sharks, while in waters cooler than that, fisheries tend to catch dolphin fish. So I then used the same framework and I applied it to a demersal community in an oxygen minimum zone. And here I expect that hypoxia tolerance and oxygen are going to be the main factors that are causing changes in catch composition. I based this analysis on a more local scale sampling or data. And here I sampled we sampled, Andres was actually there too, right, Andres? Along the Pacific coast of Costa Rica between 150 and 350 meters between 2008 and 2011. And we were lucky enough within this time frame to be able to capture El Niño, La Niña, and neutral conditions. And this is a really useful way to create a natural experiment to understand how warming and deoxygenation affects marine communities in cases where you don't have long time series to be able to evaluate these impacts. So not ideal, but getting a little creative to be able to get any information that we can. So how this works is that during El Niño conditions, the thermocline deepens, and so we have warmer waters with higher oxygen levels. The upwelling intensity is much less and much lower. And during La Niña conditions, we have cooler waters with lower oxygen levels because the thermocline actually shows closer to the surface and upwelling intensity increases. The way we're going to interpret the two indicators here is going to change a little bit, and that is mainly because temperature and oxygen are actually positively correlated within oxygen minimum zones, in contrast to pelagic environments. So here, MODC would represent the hypoxia tolerance in a fish adapted to low oxygen minimum zones. And I would expect that the oxygen demand of species within oxygen minimum zones would remain low. I would expect that species would be very hypoxia tolerant within these regions. But then when we get to the bordering areas, such as oxygen limited zones, where the oxygen concentration begins to increase, then I would expect the oxygen demand of species within the catch to increase as oxygen increases. As a consequence, the aerobic habitat index of the catch would increase within oxygen minimum zones as temperature increases, because the oxygen demand of species remains low and stable. As we get out of the oxygen minimum zone, past the threshold, then the aerobic habitat index can increase, but at a much slower rate, or even plateau, as species with higher and higher oxygen demands are going to begin to be present within the community. So I found that species depth centroids, or the depth at which the highest abundance of these species were found, shifted between neutral Niño and Niña years. So the strongest difference was found in Niña years, where oxygen minimum zones expand. So oxygen minimum zones expand and they force species towards shallower waters. And this fact that species depth distributions track the changes in temperature and oxygen so closely means that they're probably living very close to their physiological tolerance limits, and therefore are probably very sensitive to any further changes in temperature and oxygen. And these are the graphs showing how the mean oxygen demand of the catch changes with oxygen and temperature within oxygen minimum zones. Here, oxygen is the main factor driving changes in both indicators, but we also see the presence of an oxygen of a threshold. So within very low temperatures, the oxygen demand of species remains low, and then it begins to increase after reaching a threshold. And the aerobic habitat index of the catch increases within oxygen minimum zones until you reach the threshold, and then it plateaus. So basically what we were expecting. And so I would just like to leave you with these three main messages. So we know that temperature and oxygen are shaping the catch composition of fisheries within the Eastern Tropical Pacific. This means that with further changes in warming and oxygen in the region, that these are probably going to force further changes in catch composition for these fisheries. While temperature is the main factor shaping the composition of pelagic fisheries in the surface area, oxygen seems to play a bigger role in the demersal community and within oxygen minimum zones. It is, well, we know that the ocean is warming and losing oxygen not only in the Eastern Tropical Pacific, but throughout the entire world. And we can use this new framework based on the Aerobic Habitat Index to study the impacts of warming and deoxygenation on marine ectothermic organisms. Thank you all very much for listening, and thank you.
Thank you very much, Taylor. We have time for a few questions, so if someone has a question, you can either unmute yourself and ask, or you can put it in the chat and read it.
I have a question. Can you hear me okay, Taylor?
Hi, Tyler. Thank you.
Hi, Taylor and I were in the same group together at UBC, so it's nice to see you in video format for at least a portion of the talk. Yeah, my question, it was cool to see the results, and congratulations on successfully defending your PhD. I was just curious how you might suggest you would interpret your results based on some of the trophic reorganizations that we might expect to see as different species move to different locations. So I know the species distribution modeling approach takes into account the environmental conditions as they change, but how would you expect your results might be influenced by the impact of food web interactions and trophic relationships?
Mm-hmm. I think I'm very excited to explore this topic. I think that the results as is, I wouldn't expect that you would be able to get much information about how trophic interactions change. But I do think that the Aerobic Habitat Index could be used as a driver for seeing changes in species distributions, or I don't know, maybe even abundances if we find out that would hold in the future. And we could use those as drivers for ecosystem modelings to further explore how warming and deoxygenation can affect trophic interactions.
Cool, thank you.
Mm-hmm.
I have a question. You mentioned that you in your index you used Baumgarten-Lanfy parameters to estimate, I guess, the oxygen demand. Is that right?
Mm-hmm.
Okay.
Mm-hmm. Yes.
And what happens, because this is a fixed parameter and growth is also changing under warming conditions. So how would that affect your index?
Mm-hmm. I think that's another area that I would be very interested in exploring. But as it is, we do have a parameter that adds, temperature dependence to size and to growth. So growth would change with temperature, but the temperature dependence parameter is fixed. And so far, we've seen that comparing several different species, that the projections of habitat loss are very similar. But we also know that temperature is one of the most important factors driving the changes in the aerobic habitat index. And and it can vary, temperature dependence between species can vary quite a lot. And so one of the next steps that I expect to take is to be able to get more details in this temperature dependence and how it affects all the parameters within the index, including growth. while still keeping data requirements low. And this could be done in several ways. So one of the things that I would like to explore actually is to see how to associate different growth rates with different temperatures and see how growth changes with temperature, and include that temperature dependence into the model.
Thank you. Any other question? No, if there's no more questions, then thank you very much, Taylor, for this very interesting talk. And thank you all for being here, and sorry for all the technical difficulties. And we hope to see you next week in our, I think it'll be our last seminar of the season, so of the year at least. So thank you very much.
Thank you very much, and sorry about the technical difficulties.